Okay, so today we're going to specifically look at confidence intervals for sample proportions. Okay, so the point estimator here is going to be, so we want to know that um, the point estimator here is going to be the sample proportion, right? So whatever I took a sample, the proportion of the sample that has the characteristic is my estimator. Now we're going to get a critical value, and we'll talk a minute about what that is, and that's going to be this z star. Okay, so you can take the point estimator plus or minus some critical value times some estimate of the standard deviation. So we're not actually going to get the standard deviation for the population here, but we're going to get an estimate for it. And what we're going to do is we're actually going to use, assuming that the sample proportion is pretty close to the actual proportion, we're going to use the sample proportion as our stand-in for the p in the standard deviation formula for the population. Okay, so I'm gonna say this is like my formula here for the confidence interval, right? So you're gonna get two numbers. You're gonna get this minus this, and then this plus this. Okay, and this number, the z, is going to be determined by my level of confidence, right? So how confident that I am that the actual, what do you call it, population proportion lies within this interval, okay? So we're going to give an example here, right? So we're going to say we're going to take a sample of 251 beads, okay? And in that sample, I have found 107 red beads, okay? So this means that my sample proportion is going to be 170 out of 251, which is approximately 0.426. Okay, so I now have this number, okay? Now, the second thing that I need is this number, right? My estimate for my standard deviation, which I have the data that I need for, right? So this is going to be the square root of the sample proportion, which is the 0.426 times 1 minus 0.426, which is 0.574 over the sample size, which is 251. If you throw this in a calculator, you're going to get something pretty close to 0.031. Okay, so I have 2 out of 3 of the numbers in my puzzle here. Okay, so where is this critical number coming in? Well, that's going to be determined by my confidence level. So we're going to hunt for a confidence level of 95%. I want an interval that I have a 95% chance that the actual proportion of the population lies on that interval. Okay, so here's the thing. If I assume that p hat is distributed normally with the mean of p hat and the standard deviation of p hat, then I have 95% tells me that, like, the z-score has to be within 2 standard deviations, okay? If I use the empirical rule, I can say that z star is approximately 2, because 2 standard deviations from the norm is 95% of the data points, right? Now that 2 is an estimate, and I want to show you that you can actually get a little bit closer than the 2 on that, because if you think about your bell curve, okay, so here's my bell curve, right? And I want to know where is actually 95% going to be here. Well, then 5% has to be in the tails. So this is 2.5% over here, and this is 2.5% over here, which means that I want the z-score that corresponds to this. So negative z star is going to be the z-score that corresponds to this. Well, that's not hard to find. I just grab my calculator, right, and I go second, invert the norm. What is 0.025? I obviously just did this recently. 0, 1, because those are z-scores. mean of 0, standard deviation of 1, do the left tail. That's going to give me a negative value, and that's okay. But the negative value is 1.96. Okay, so the real z star is much closer to 1.96. Okay, so if you don't have a calculator handy, you could use 2 for 95% because it's really, really close. But the actual number is 1.96. So let's just go ahead and calculate this interval. If I calculated the interval with 2, I would get 0.426, because that's my p hat. That's here, right? Plus or minus the z star, which I use 2. That's here, right? Times the standard deviation gain, which is this one, right? 0.031, which, okay, so if I put the minus and the plus in there, this is going to give me an interval between 0.364 and 0.488. Okay, that's pretty good. So I know that the actual proportion of this population of beads that are red is somewhere between 36.4% and 48.8%. Pretty tight. If I use the more accurate z, I'm going to get 0.426 plus or minus 1.96 times 0.031. And you can see it's not going to make a whole lot of difference. If you throw that in the calculator, you're going to get 0.365 to 0.487, which narrows the thing by 2 1,000ths of a unit, right? So 0.2%, right? Which is a little bit more accurate, but still it's really close in the same range. Okay, so this is how you would do this by hand. Now, real quick, the calculator is set up to do this. Okay, so really all I need is my n, my x, and my confidence level. Those are the 3 key endpoints. And x and the confidence level. How many in the sample? How many in the sample have the characteristics? What's the confidence level of the interval? Why? And then go to my calculator, and this is actually a built-in function. Go stat, go over to tests. I have a 1 proportion z interval. Z meaning it's normal. 1 proportion z interval. I hit enter. It says, how many are in the sample? Well, let's see. How many were in the sample? There were 251 in the sample. Then I put 2, 5, 1. All right, no. There were 251 in the sample. That's the n, 251. 107 of those were red. 95% confidence interval. I calculate, and boom, there comes the number. 365, 487, just like I did with the 1.96. And it tells me also what the p hat was for the sample and the sample size. So the calculator will do this all outright. That is under stat test 1 proportion z interval. So there you have that. Now, does this always work? Okay. So here's where we could have a bit of a challenge. All right, so let me bring up a new. We need to have 3 conditions that are met. Okay. 1. In order for us to verify p hat as a valid point estimate, the sample must be random. So we will call this the random condition. Ideally, it's a simple random sample. Okay, but it has to be random. Number 2. Okay, in order for us to validate the the idea that we have normality, right? So in order for this to work, we have to assume that the z star works. We have to have normality, right? Because that's coming from an invert norm reality. Okay, this is where you have to have large counts. Okay, so in order to assume normality, we have to have large counts. And we can let the p hat stand in for the indicator here. So we're going to measure p hat versus n has to be greater than or equal to 10, and 1 minus p hat times n also has to be greater than or equal to 10. Okay, so this is how we get normality, is through large counts. We get the validity of the estimate through randomization. And then finally, we can utilize we can depend on the standard deviation. So that one requires the 10% condition, which means n has to be less than 10% of the entire population. Okay, so let's think about this. Did we meet the 10% condition? In this, well, the population was the population of beads, so all the beads in the population. Not so sure how many beads were held in total. So if there were more than 2,510 beads in the population, then we would have met this. So this is probably the one that is most in challenge in our example here, right? Okay, so just being aware that you have to have all three of these. Now I want to note that we're substituting the p hat here, here, and in the standard deviation estimate, we're using p hat times 1 minus p hat over n. Now, this actually has a name, okay? This thing is actually not referred to as the standard deviation, but is referred to as the standard error. Okay, or another way of saying that is SE of p hat. Okay, so the margin of error is equal to the critical value, right? The z-score, the standard score, times the standard error. Okay, so that's kind of what this is, and then remember your confidence interval is the point indicator plus or minus the margin of error, right? So there you go. This is confidence intervals for proportions, and we'll do some practice with these next class.